How does one study an earthquake? We start out with seismic wave types. P waves, also known as primary waves, are the first waves to arrive. These are compressional waves. S waves, or secondary waves, arrive second. These are back and forth waves. They wiggle. And then we have surface waves. These surface waves distort the surface of the Earth and travel only along the surface of the Earth. These seismic waves are going to be generated at an earthquake focus, arriving at a seismograph at some distance from the earthquake. It doesn't have to be far. Now, if we measure the nearest expression of the seismic wave, it will be right above the focus. And that's called the epicenter. So all waves are going to travel from the focus, both the surface waves after they reach the surface and the body waves that are traveling through the body. When we see them arrive at a seismograph, at a station, there's going to be a deflection. So as the Earth moves around that weight that serves as the marker in the seismograph, there's going to be a wave generated. Either it's going to go up first or it's going to go down first. If it goes up first, this means the wave is approaching. If it goes down first, it means it's going away. We'll come back to that in a few minutes. You notice the difference in amplitude here. So the P waves arrive first, but they're relatively low in amplitude. S waves arrive second, a bit higher in amplitude in this diagram, and then the S waves arrive much later with a very large displacement on the seismograph. Now we're going to take a look at the Earth and we're going to shake it, and we're going to examine the differences between the different types of waves that are generated, the different types of seismic waves that are initiated from the earthquake event. These shifting rocks in earthquake cause vibrations called seismic waves. They're going to travel through and within the Earth. Scientists use seismographs to record this data. This data in turn informs us about the earthquake, and it also tells us about the interior structure of the Earth, as we saw earlier in the course. There are two basic types of seismic waves: body waves and surface waves. Body waves travel within the body of the Earth. These include primary or P waves and secondary or S waves. P waves cause the ground to compress and expand. It moves back and forth in the direction of travel. They're called primary waves because they're the first type of wave to arrive at any recording station. P waves can travel through solids, liquids, and gases, like sound waves. S waves shake the ground in a shearing or crosswise motion that's perpendicular to the direction of travel. They move back and forth. These are the shake waves that move the ground up and down from side to side. They're called secondary waves because they arrive second, after the P waves. Unlike P waves, S waves can travel only through solid materials. After both P waves and S waves have passed, they're followed by surface waves which travel along the Earth's surface. These surface waves can only travel through solid material. They're slower moving than body waves, but are much larger and therefore more destructive. There are two types, known as Love waves and Rayleigh waves, after the scientists who first described them. Love waves have a horizontal motion that moves the surface from side to side, perpendicular to the direction of the wave travel. Of the two surface waves, Love waves move faster. Rayleigh waves cause the ground to shake in an elliptical pattern, in a motion similar to that observed in the celerity of an ocean wave. Of all the seismic waves, Rayleigh waves are the longest, and this gives them the longest duration on seismic recordings. When we look at these things in 3 dimensions, we can see the P wave motion here. P waves, again, primary waves, are compressional waves that travel quickly through rock. So this is like banging on a surface with a hammer. That hammer strikes the surface, and that compressional wave is going to travel through that material. So the P waves are going to travel as a series of contractions and expansions. They're going to push and pull particles in the direction of their path of travel. Now the red square here charts the contraction and expansion of a section of rock, or a given block of rock. As the wave approaches, it's going to compress that rock. As it passes, it's going to stretch that rock out again. This is going to happen over and over again in a given seismic event. S waves, on the other hand, secondary waves, travel at about half the speed of primary waves. And here, we're going to see a displacement of a block of rock. So these S waves are shear waves that push material at right angles to the path of travel, just like waving a rope or a garden hose, or this time of year, shaking your extension cord out of the snow to plug your car in. This red square is going to show how a section of rock shears from a square to a parallelogram as the S wave passes. So it's going to deform. It's not only going to rise and fall, but it's going to deform in place. Now, surface waves ripple across the Earth's surface where the air above allows for free movement. There's no confining pressure above the surface. So this means there's a freedom of expression here. In one type, the ground surface moves in a rolling elliptical motion that decreases with depth beneath the surface. This would be called a Rayleigh wave, moving in elliptical motion. In the second type, the ground shakes sideways with no vertical motion. This would be called a Love wave, whereas this would be called a Rayleigh wave, moving in elliptical motion. This is called celerity when talking about waves in an ocean or a lake. So seismic waves are going to be used to locate an epicenter. An epicenter, again, means on top of the center, or on top of the focus in this case. So the focus is where the slippage occurs in the Earth's crust. The epicenter is the point on the surface above that focus. Now, to find the location of an earthquake, we're going to need at least 3 seismographs. The P and S waves are going to arrive from 3 seismographs. Knowing that P waves travel at a rate that is faster than S waves, we can calculate the distance from the seismograph to the epicenter. We can't necessarily determine where the epicenter is unless we have 3 seismograph data sets. So we're going to graph the distance of travel versus the time elapsed. Because P waves travel twice as fast as S waves, the interval of time between their arrival increases with distance. By matching the observed interval to known time travel curves, a seismologist can determine the distance from the station to the quake epicenter. Again, this is the distance to the epicenter, not where the epicenter is. And that's going to be regardless of how far the seismograph is from the focus. There's going to be a difference in arrival times that's going to be equated to a distance. So 11 minutes equals 8,600 kilometers. An 8-minute interval is equivalent to 5,600 kilometers. And a 3-minute interval between the P and S waves implies a distance of 1,500 kilometers. Now we can measure the amplitude of the largest seismic wave, in this case 23 millimeters. The time interval between the P wave and the S wave arrivals, 24 seconds, to determine the distance from the epicenter to the seismograph, in this case 210 kilometers. By plotting the 2 measurements on these graphs and connecting the points, the seismologist can determine the Richter magnitude of the earthquake to be 5.0. If the seismologist then draws a circle with a radius calculated from the travel time curves around each seismographic station, we'll have 3 great circles. One that's 1,500 kilometers in diameter, one that's 8,600 kilometers in diameter, and one that is 5,600 kilometers in diameter. So the earthquake took place here, beneath San Francisco. A station in Denver, 1,500 kilometers away, records this time travel differential. Another station in, this is probably San Jose, Costa Rica, says 8,600 kilometers away. And then Hawaii, 5,600 kilometers from this. We put those 3 great circles on a map of the globe, and we get San Francisco as the epicenter. Why do we do this? What's the point? It seems like a lot of work. Well, we need to measure the size of an earthquake to determine how dangerous this earthquake is going to be. And because there's a wide range, essentially from nothing to very, very big, we need some kind of scale. And this led to the development of the Richter magnitude scale. It's logarithmic, so every time it goes up 1, the ground movement increases by a lot. This is based on the largest ground movement. The moment magnitude is also a logarithmic scale. It's proportional to the product of the area of faulting and the average fault slip. So it's the size of the displacement. And then we have the shaking intensity. The intensity scale is related to damage and the human experience. What's it like to be in this type of earthquake? So that shaking intensity is going to differ depending on what you're standing on, the type of rock or sediment or even water, and the shaking, the violence that's done to that place you're standing on. When we discuss magnitude and frequency, there's a clear relationship in which we have many small earthquakes, thousands and thousands of small earthquakes occurring all the time. Fortunately, we have very few large earthquakes, very few large, massively destructive earthquakes. Any discussion of earthquakes has to include a discussion of the big ones. The biggest that we know of, the biggest that we're aware of in human history, is the Great Chilean Earthquake of 1960. It occurred on May 22nd in 1960. Again, coincidence? Most likely. And it is known as the most powerful earthquake recorded. Generally, it's considered to be about a 9.5. So when we put these together, the big earthquakes with some other energy equivalent here, on a logarithmic scale, we can see the true size of these big earthquakes. The Chilean earthquake standing out at the biggest, 9.5. Just behind them, at around 9.2-ish, are the Sumatra earthquake of 2004, occurred right around Christmas time, and the Good Friday earthquake of Alaska in 1964. These are both bigger than the Krakatoa eruption in terms of energy equivalent or energy release. And of course, the Chilean earthquake is much bigger than those two. Now, next on our hit list is the world's largest nuclear test. This is the Tsar Bomba of 1961, Soviet nuclear test, where the weapon was dropped on the sort of banana-shaped island north of Archangel in Siberia, which is now open to tourism, by the way. Just slightly behind the Tsar Bomba is the San Francisco earthquake of 1906 that we discussed earlier. That's about equivalent to the Mount St. Helens eruption. So a fairly minor eruption is equivalent to one of the largest earthquakes in North American history. Just behind the San Francisco earthquake of 1906 is a series of quakes that you probably haven't heard of. If you're from Missouri, you've probably heard of them. If you're not from Missouri, you probably haven't. This is New Madrid. Because it's Missouri, it's not Madrid, it's Madrid. And this is why St. Louis is called St. Louis instead of Saint Louis. So in Missouri, in 1811, December 16th of 1811, there was a major earthquake on an old fault. This is a failed rift where North America tried to split apart and it failed. This failure persists, though, in the deep crust of North America and occasionally becomes active. It became active for a few months between the end of 1811 and the beginning of 1812. There were aftershocks for years after that, though. More recently, the Loma Prieta, California earthquake in 1989. This disrupted the World Series at the time, which was being held in San Francisco. Kobe in 1995, also a very large earthquake. And Northridge, California, another well-known large earthquake. These are all larger than the atomic bomb dropped on Hiroshima. Another earthquake probably haven't heard of that's famous is the Long Island, New York 1884 earthquake. Now this is significant because it's in New York City and because it's a fairly stable portion of the continent. And then just working our way down, an average tornado, whatever that might be, large lightning bolts, something we've all experienced. Oklahoma City bombing of 1995. This is when McVeigh and Nichols blew up the Murrah office tower in Oklahoma City, and then an average lightning bolt here. So as we go down the scale in magnitude, we go up very dramatically in number. The big things are rare, small things are common. When we talk about intensity scale, this is an experience scale, or how we feel about a given earthquake. At an intensity level of 1, people don't feel the earthquake. At an intensity level of 2, a few people are going to feel the earthquake. If you're in a quiet, stable room on the ground floor, you may see lights swinging above you. Intensity level 3 can be felt indoors, where again it's quiet. Most people don't think of this as an earthquake. If you're in a parking lot, you may see the cars move slightly. Now, the cars are going to be acting like that weight in a seismograph. They're going to tend to remain stationary as the earth moves around them. The suspension of the car is going to allow it to maintain its station as the earth moves back and forth beneath it. Now, intensity level 4, felt by many indoors, felt by a few outdoors. This is when dishes and windows and other parts of your house may rattle. Parked cars rock noticeably now. I've been in a few of these, and 4s and 5s. I've always been in a place where there's too much going on, so I didn't notice it. Or if I did notice it, I thought maybe it was a truck going by or some other local civic catastrophe. So a 5 is felt by most. People will wake up if they were sleeping. Dishes and windows can be broken. Unstable objects can be overturned. Number 6 is felt by all. Heavy furniture moves. Damage is generally slight. 7, slight to moderate damage in well-built structures. Considerable damage in poorly built structures. Some chimneys will be broken. Masonry buildings are going to suffer damage fairly consistently in this type of earthquake. A number 8 intensity is considerable damage in well-built structures. Damage is great in poorly built structures. Chimneys fall, factory stacks fall, columns, monuments, and walls collapse. A 9, damage is great even in well-built structures with partial collapse. Buildings can be shifted off their foundations. A 10, now it's getting really catastrophic. Even well-built wooden structures can be destroyed. Most masonry and frame structures are destroyed, and railroad lines are bent up. And at 11, few if any masonry structures remain standing. Bridges are destroyed, rails are bent greatly, and at a 12, damage is total, lines of sight and level are distorted, objects are thrown into the air. That's a pretty spectacular earthquake. Now, the New Madrid quake, again, the first big one was December 16th, 1811. It's depicted here in an article that was written a couple decades later, 1851. At least it was published then. New Madrid is located right here. This is in what's called the boot heel of Missouri, the little boot heel shaped thing that sticks down into Arkansas or towards Arkansas. So the slip occurred here. The focus was here. And you can see the intensity scale persisting all the way up into New England and Ottawa in Canada. So Montreal would have felt it. Quebec City would have felt it. All over the eastern U.S. Colonizers from Europe weren't living out here at the time in any significant numbers, so there are no reports from their perspective. One of the more interesting features or phenomena of this eruption are the sand blows, which were kind of like sand fountains of sand blasting out of the ground. Here we can see the original soil horizon with the sand blows, the dikes that form the sand blows introduced. You can see the sand rising from the feeder dikes. Ultimately, this whole feature is going to be covered with sand that's deposited by subsequent floods of the Mississippi River. We can date these materials by radiocarbon dating organic material that gets wrapped up, that gets deposited within the sand blow. It's not particularly accurate, but provides us with some idea. Now, when we look at a rupture of a fault, it's not just the movement, the displacement in terms of distance. It's the movement, the displacement in terms of area of displacement, area of rupture. Depicted here, the magnitude 4, we have 1 square kilometer of rupture. A magnitude 6 would result if there's 100 square kilometers of rupture. And 8 would occur if there's 10,000 square kilometers of rupture. So this is close to what the San Francisco earthquake was in terms of both the area of rupture and the magnitude of the earthquake. So again, when we look at the distance of displacement, magnitude 4, we'll see a displacement of 0.05 meters. Magnitude 6, displacement of 0.5 meter, and a magnitude 8, a displacement of 5 meters.